Giove, Juno, Programma New York,
There are many theories about the origins of Jupiter. Here's what we think happened. Nearly 5 billion years ago, a star in our galaxy exploded. The explosion caused a nearby cloud of gas and dust to collapse and flatten into a spinning disk. Most of the gas and dust collected into a hot, dense core that became our Sun. The remaining debris formed the planets and other small bodies in our solar system. And the majority of that debris came together to form the giant planet Jupiter. Of all the 8 planets, we believe Jupiter formed first. Understanding the formation of Jupiter is essential to understanding the origins of our entire solar system, the formation of Earth, and the most basic foundations of life as we know it. Jupiter is 1,300 times the volume of Earth, more than twice the mass of all the other planets combined, the 5th planet from the Sun, and the largest planet in our solar system. Because of its enormous size and powerful gravity, it is believed that Jupiter has influenced the formation and evolution of the other bodies that orbit our Sun. Unlike Earth and the other smaller planets, the composition of Jupiter has remained unchanged since the solar system began. Like a time capsule, Jupiter can help us reconstruct nearly 5 billion years of history.
In Roman mythology, which of course is rooted from Greek mythology, was Zeus, and the Greek name for Juno was Hera. So they were companions, and Zeus, of course, was but of course Juno was a fairly powerful god herself, and she saw enough that she said, okay, I'm suspicious, and kind of traveled down and used her powers to look right through the clouds and see the true nature of Jupiter and understand what he was really up to.
Hundreds of scientists and engineers in 5 countries have been working for more than 10 years to design and build the Juno spacecraft.
Universe simulator in the clean room to pretend it's launch day. Juno has a very complex instrument suite. Dressing up in bunny suits and putting in a clean room that's changing air as fast as we can do it and trying to keep it as clean as possible, but nothing's perfectly clean. Make sure we understand the differences between the environment we have on the ground and the environment we have in space. It's a blast to march through that testing suite and make sure that a real piece of hardware that is going to fly all the way to Jupiter. So if it was just us scientists looking down our microscope, it wouldn't be so much fun. Scientists, engineers, administrative people, technicians, people who do purchasing. I mean, it's amazing how many people, and it's amazing that when you get that kind of atmosphere and that kind of collaboration and synergy, how to dive in and work whatever needs to be worked. I think that it's a tremendous experience to be involved in something where we can learn about how a lot of people working on something takes a long time to prepare. There's an opportunity to be really anxious. There's an opportunity to be really excited. A bunch of pieces. We had what was known as the prop module. That's the large base piece of the structure. On top of the prop module sits the vault. Individual boxes, flight computers, our power subsystem, all scenario scenarios, just like in flight. We verify it functionally does what it's supposed to do. So in order to accurately solar array deployment test, we have very large solar arrays on this spacecraft, so that once we get to Jupiter, we have enough electricity to operate the spacecraft. In order to be able to then deploy them with low friction, we use a flat floor and pneumatic devices kind of like a hovercraft. We've modeled it, we've tested, we have a good idea of what will happen. We will put it in a large chamber that tries to replicate space. Also within the chamber is a shroud that is filled with liquid nitrogen, tests its experience in space. So we get through these major environmental milestones, verify that the spacecraft is working as we planned, that it functionally works after we do all the tests, and we prep it to ship down to the launch site. Our launch of course, some of those cameras really do feel like my babies that I've been working on for such a long time. We put it together and we let it fly. There's nothing like, let's just shake people's hands and walk away proud of working this mission. I don't know what else knows how to work together the way that this team does. It's such a fun job, and it's really a wonderful, wonderful way. We'll do all the launch processing, and then we will go ahead and launch it. So it's in the sky, but we have to do with what we have. There are weather rules in place, weather criteria that we cannot violate. There are rules for cumulus cloud. We will power up the spacecraft for the final time. Not only do our capabilities complement each other, but our enthusiasm infects each other. And I, as a 14-year-old, stay out until 4 in the morning to watch the guys walk on the moon. And I expect we'll be following everything that's happening with Juno. It's a great... The short answer for why Juno is solar-powered rather than nuclear-powered.
Right now, we're looking at how we can understand what the environment is actually doing to
Power source.
We haven't taken solar panels that far before and run an entire spacecraft that far from the sun.
escaping the gravitational pull of Earth, Juno is still held to its trajectory by the sun's gravity. The Juno spacecraft is carried 50 million miles into space, as far as the orbit of Mars. A burn from the main engine directs Juno back toward Earth for a final encounter with its home planet. Using Earth's gravity for energy, Juno slingshots into space, increasing its speed and receiving the boost it needs to pull away from the sun and coast all the way to Jupiter.
As we get further and further from the sun, that amount of energy will drop off until we finally get to Jupiter, where we're only generating 400 watts. It's not even enough to run a hairdryer. The rings of Saturn are very well known. They're this gorgeous set of rings circling the planet, that they're so bright and that they're so easily seen. It's Voyager spacecraft. Before that, we didn't know that Jupiter had rings. They're
satellites that Jupiter has moving around the planet close in. These satellites from their surfaces, and that dust forms the rings. When you get close up with the spacecraft, they're obviously easier to see. You might worry about Juno running into some of these rings.
That kind of look a little enough like Earth that we're thinking, well, maybe there is a life that we would recognize there. Europa, one of the moons of Jupiter, and find life and then not be able to tell. Jupiter has such a strong radiation environment that when you send out like sensors and testing for the Jovian radiation environment on Earth is not easy. You have to go to a very high energetic electron facility, which is a very rare.
The dramatic thing about Juno is the orbit.
In order to slow us down, there's so little time to react that we have to let it do its own thing. And despite different longitudes as Jupiter spins underneath us, it does mean that Juno is going to see multiple channels to try to study the composition of an atmosphere, especially a giant planet like Jupiter. And that's when you need
Disprove theories about the types and amounts of materials that contribute to the composition of Jupiter. By peering beneath its clouds and discovering what Jupiter is truly like, Juno will also test our ideas about the formation of planets, as well as other major secrets of our solar system. Measuring the amount of water in Jupiter will help us understand how and where in our solar system the giant planet formed. In our quest to unlock the history of the planets, Jupiter is the gateway, and Juno holds the key. On August 5, 2011, one of the world's most powerful rockets is set to take off. The Atlas V 551 rocket, weighing 650 tons, launches and reaches a top speed of 4,500 miles per hour. The rocket hurtles through Earth's atmosphere, exhausting its fuel and reaching orbit in just over 10 minutes. The payload fairing falls away, revealing the Juno spacecraft within. Once in its proper orbit, the Centaur booster gives the probe its spin and sets Juno free on its journey to Jupiter. In the shadow of our planet, the spinning Juno spacecraft deploys its 3 massive solar arrays, which will power the mission for the next 6 years. After these arrays lock into place, power from the Sun streams into the circuits of Juno for the first time.
Trajectory, which is on a path relative to the Sun originally, now is flying by the Earth and is also influenced by the Earth's gravity field. It gets deflected out towards the planet Jupiter. The idea is that
After 5 years of being alone in space, Juno approaches Jupiter and begins reaching a top speed of 160,000 miles per hour, officially becoming the fastest man-made object in history. The main engine ignites to slow down the spacecraft, and Juno is captured by the powerful gravitational pull of Jupiter. Settling into the most challenging orbit ever attempted, Juno will come as close as 3,100 miles to the planet's cloud tops. Juno will continually duck below deadly radiation belts as it studies Jupiter in unprecedented detail for more than a year. Juno will use remote sensing to inspect Jupiter from its innermost core to the outer reaches of the magnetic bubble the giant planet inhabits. Juno will be the first probe to visit the regions above the poles of Jupiter, witnessing energies in the magnetosphere that create its extraordinary ultraviolet auroras. After orbiting Jupiter for over a year, the Juno craft will dive deep into the atmosphere and burn up. But the mission will never truly end. No matter how many answers we find, there will always be more questions. Our search for understanding and meaning continues.